Hi, everyone. I think we're all here, so let's get started. Welcome to Advanced Operations and Features with Ryan Lambert. This final session focuses on PostGIS, scratching the surface of a range of the advanced features that PostGIS is capable of. Today's session will cover preparing data in different formats, such as GeoJSON and MVT for external dependencies, 3D rendering, and routing. My name is Lindsay Hooper, and I'm one of the Postgres conference organizers. I will be your moderator for today. I'm here with Ryan Lambert, as I said earlier, who's the owner of RustProof Labs. Ryan's been working with GIS since 2011, and he got his start in working with PostGIS when, on a quest to update a roadmap, he started using PostGIS, Postgres, and OpenStreetMap. He has since been a contributor to the OpenStreetMap project for the last 5 years. Ryan's given many talks on PostGIS, and he's currently working on a book on how to use PostGIS and OpenStreetMap together. A few logistical notes. I've gone ahead and put you all on mute in order to avoid background noise, and we encourage you to ask questions. You can do that through the chat function at the bottom of your screen, and questions will mostly be answered at the end of the training, although pressing ones should be answered in the moment. We're expecting the session to run just around an hour, and it will be heavy on the demo. So with that, I'm going to hand it off to Ryan and enjoy.
Hi, everyone. Thank you, Lindsay, for the introduction as always. And thank you to PostgresConf again for hosting this entire webinar series. And of course, thank you for everyone who has joined us live for today's talk. It's going to be a lot of fun. So today we are on the final of a 6-part series. It's really exciting to me because one, this is a really fun session for me. And also it represents me closing out a very big project. So it's always nice to write something off and check something off the list. The whole series so far has been published. The videos, recordings are online. And the link at the top of this page has the intro video as well as links to all of the other videos for this series. And after today's session is done, I'll get the video cleaned up and published as well in the same format. So today's agenda, we're going to spend a little bit of time talking about extensions beyond PostGIS that integrate with the PostGIS functionality and take it a step further. I'm going to spend a decent amount of time going over some functions and features that I personally find cool. And then we'll spend the majority of the time working on a demo using OpenStreetMap roads data and PG routing to get us from point A to point B. On the note of the demo, I have made the demo data available, and I'm going to copy and paste this link right here into the chat so it's easy for everyone to get to that page while we're going. There is a download. It's just under 3 megabytes for a small extract of OpenStreetMap data. And there's also a link to download the SQL script that I'm going to be walking through in that demo session. So you can download the data, you can download the code. A lot of times it's easier to follow along, especially with these complex queries. If you can get the code up on your own screen and focus in on the snippets of code and zoom in and scroll as you see fit. So that is all available and will continue being available once the video is posted as well. So PostGIS itself is a lot of fun. There's a lot of great, powerful functionality that's built into the core PostGIS extension. But that's only a part of what we can do. There are a number of other extensions in the PostGIS ecosystem that can be added on to further enhance the functionality of your spatial databases. One note on the top item there, the PostGIS roster extension, that is only split out as of PostGIS 3 and newer. So if you're using PostGIS 2.5 or prior, the roster components are built into the core PostGIS extension. But as you move into the newer versions of the extension, you'll have to install those components separately. Another key piece that extends PostGIS is the PG routing extension, and we'll be spending a good amount of time working on a demo to put this extension to use today. when I look at these extensions, one way to kind of look at how much is packaged with each extension is to take a look at the number of functions included with each extension. So this kind of gives a breakdown of some of these more popular add-ons to PostGIS with an idea of how much additional functionality comes along with it. And now, to be fair, counting extensions in a database is sort of like counting lines of code in any other programming language. It's only useful to a certain extent. So take it with a grain of salt because one function can do a lot or a little. So just counting the number of functions itself is a fairly shallow indicator of functionality. But it is a good way to get kind of an idea of what's involved in each of these additional components of PostGIS. Now on to some functions and features that I personally find cool. And when you brand something as advanced, it's always a little bit of a risk because it's hard to know what is advanced to everyone. And so some of what I'm focusing on here is just simply neat things that you may not have otherwise encountered. In any database, you need to be able to ensure some level of quality. And PostGIS gives us some quality control functions. We have the ability to check our geometries to ensure that they are valid geometries. And that first function on the list will just return a Boolean true or false for each geometry. So if you want to get down to just the invalid geometries, you can set your filter that way and get down to it there. And then the second function will actually tell you what's wrong with the geometry from the PostGIS perspective, so you can look at your source data and hopefully remedy the situation and get to valid geometries in your database. Some more geometry quality control functions are available. You can check to see if your data is closed. You can check your polygons for what method of winding they used, whether it's clockwise or counterclockwise. And if you are using OpenStreetMap data, you may notice that all of your polygons are counterclockwise. And there are two standards. There's half of the standard world uses counterclockwise winding for the polygons. The other half uses clockwise. So depending on where your data comes from and where you need it to go, you may need to pay attention to what directionality is in your polygons. So these are available for you to look at. And there are a number of other what I would consider quality control functions. And so if you look for function names that start with st_is, that'll get you a good list of other functions inside of PostGIS that can help you kind of look at the quality of the data and work on bringing the level of quality up. Another way of enforcing quality control, a little more specific, is with addresses. If you have street addresses, you often need to get them into a more standardized format, and luckily we have some extensions that allow us to do this. The first one here is the address standardizer extension. It does require that you also install some data. The data_US portion is included by default. If you are outside the US, I'm not certain exactly how you need to go about getting those rules and that data set, but I assume there's a little bit more documentation around that. I personally haven't had the need to standardize international addresses, so I haven't gone down that rabbit hole yet. But this is here, and when you run the addresses, your street address, through an address standardizer, you're going to get back a tabular result set. It's going to parse the data, standardize it based on its ruling, and then spit out some data on the other side. And in this case, we get this STD ADDR result, and the docs have more information about what all this means. One of the key things I take away from this is I notice things like street is spelled out in full instead of being abbreviated as ST. Also, Colorado, so our state name, is also being spelled out in full instead of using the postal abbreviations that we have. So there's, it parses out the data and it puts it nicely standardized for us. The address standardizer I have more experience with is packaged with the Tiger Geo Coder extension. And it has the PAGC_normalize address. So this one, when I'm standardizing addresses, it's almost always because I want to geocode them. And because I always use the Tiger geocoder, I've always used this function that's packaged with the Tiger geocoder because it's intended to work with those geocoding functions. One of the other advantages that I see from this is it's a little bit easier. You don't have to install that second extension, and the function call is only the address. You don't have to pass in those extra parameters. The downside to that is it's less customizable, and you're really just stuck using with the standardization that they have built into this function. Now, the result from here is very similar to the previous standardized address. The main difference here are the column names are going to be different. The first one had for street name here, the prior one used just name. We also see that street is now abbreviated as ST, and our state has been abbreviated as CO. So if you have the need to standardize your addresses, take a look at the various functions that are available to us, and figure out which one is most appropriate for the needs of that you have at hand. I personally have used this one because I am doing the Tiger geocoder. Now, the Tiger geocoder is a really cool extension. This handles a lot of the underlying steps to getting the data in the first place. There are some helper processes that handle downloading the data from the Census Bureau website, the Tiger Line datasets, and it loads it into the database in the format that it needs for the geocoding. The link here is to Michelle Tobias's blog. She has one of the best write-ups that I found on the process. My procedures that I use link to her, hers as the source. Mine just has a couple changes for Linux specific setups, where her blog post was covering a Windows specific setup. So there's just a couple things you have to adjust for Windows versus Linux. But this has been a really good resource for standing up a Tiger geocoder from scratch. Now, one of the really fun projects I've had in the past few months was I had the need to create a grid and around a specific point on a map, and I wanted my grid to go out in all directions for a certain distance. And I found this combination of functions was really kind of fun to pull together. stproject is kind of the key element of this. And one thing to notice here is the first argument of the stproject function is a geography, not a geometry. Throughout this whole series so far, we've dealt exclusively with geometry data, but this function does require it to be in geography format. So we can take that, what stproject does is you take your starting geography, and then it can calculate a new point that's a certain distance, that's that second parameter, and then a certain direction, and that's the azimuth and the third parameter. So we can say, I'm here now, but I want to go 250 meters to the east. So that's kind of how stproject works. And then I'll talk through those other two functions as we go through this example code. So the end result that we're going to get to is a picture like this. We have in the very center of this grid, there's a red dot, and that's our starting point. And what I've done here is that's the center of the Coors Field polygon. And then from that center point, I wanted my grid to go out in the four cardinal directions for a certain distance. So this is the goal for the code that I had to write. And what I ended up with was this CTE, Common Table Expression query. This could be rewritten as to use subqueries. You could use temp tables or full tables. There's a number of ways you could rewrite it, but I personally like CTEs for keeping my logic together. The first part of the CTE is defining the start point. And so what this first little query does is it filters the buildings down to just Coors Field, and it grabs the centroid, or the center point of that polygon. So that's how we get a single polygon, a single point out of much more complex polygon data. And then because my project function needs a geography, I am first going to transform my geometry into the 4326 SRID. And once I've done that, then I can cast this whole thing as a geography to get it in the format that the next two steps will need. So we have our start point. That's the red dot that we saw in the middle for Coors Field. And then we're going to pass this into the west grid portion. And I really should have named this east-west grid because it goes both directions. So what we do in this step is we start with our center start point. And we're going to join that to the result of the generate series. And what the generate series does is it simply creates a series from a start point, in this case, -10 to +10 with an increment of 1. So I'm going to get a total of 21 rows, each with a single number on it, of -10 to +10 with 0 in the middle. And so this has been aliased under S. So what I do with stproject now is we pass in the start point that we want, and then we say we want to go this far, and so I'm passing in my range of numbers here and multiplying it by 250. So this sets up my 250 meter grid. And then to get the direction, you can use pi over 2. And from a geography standpoint, this ends up being east. And so we're saying we want to go, if the number here was 1, we would be saying start at the point, go 250 meters to the east. Because our series has a -10 to +10 range, we're going to get some negative numbers in there, and we get our grid out from to the west and the east from our center point. So with our west grid that has our horizontal line, our east-west line of 21 points, we're going to take that data and pass it into the last step. So we have the west grid here as our base table. We're again applying it to the generate series results. So we're taking those 21 points that went east to west, and we're applying it to another range of -10 to 10. So now when we use stproject, we're still doing a 250 meter grid that's applying to our negative and positive numbers, but the direction we have set to 0, and in that translates to due north. And so because of the negative values, we also get the south. So we get 10 steps to the north and 10 steps to the south. After this projection has happened, I can cast the data back into a geometry, which defaults, when you do this function from a geography, it goes into the 4326 SRID. And then I transform it in the outer step back to 3857. This matches the default projection for all the other OpenStreetMap data that I have in this database. So the logic that's going on behind here takes a while to absorb and kind of work through the math. I sit down with pencil and paper and I really work out what these things like this kind of mean when I'm trying to digest what's going on in this query. But then once you kind of get it figured out, it's really 15-line query or something, and it does kind of a cool thing. We can make a grid around points. And there aren't a ton of applications for this type of project, but when you have the need for something like this, and a small amount of Google Foo can get you to a functional example fairly quickly, I think that's really, really powerful. So when we're dealing with routing, which we're going to spend some time talking, a good amount of time talking about, you're going to work with a lot of line data. And lines have a number of complexities with them, especially when you have really long lines and you're trying to find a point in the middle. And what these functions here do, the first two functions work on a line. They allow you to find a point within a line. And so the idea is I'm here and there's a road over there. Where is the closest point on that road over there from me? So that's kind of what the first two functions allow us to get. And then the third one allows us to actually split the road at a specific point. And I'll show a little bit of an example of how these functions work. But if you really want to get into detailed, accurate, precise routing for the start and end points, some tricks like this are going to be very, very helpful. With our polygon data, we end up with a lot of complex shapes. In this case, I've shown a building that has a number of cutouts in the middle of it. So these are open plazas in the middle of the building that you can only access from going through the building. and they get cut out. And it's another place you'll see this is if you have a lake with an island in the middle. You'll have a polygon for your lake, but then there'll be a cutout in the middle where that island is. So you'll get a number of reasons why you have these complex polygons. And this num interior rings functions gives us a way to kind of identify those and work with them from there. Whenever you have data within a database system, one of the natural questions is, how do I get the data out and into this other system? And PostGIS has a bunch of different ways to get your data out and into other formats. Here, this list is just a number of the ones that I've used more commonly. Again, if you look through the full list of the PostGIS functions, you can look under st_as, and you'll see the full list of functions that can convert into other external formats. 3D mapping is one of the really cool things that I'm interested in. I've had just barely started scratching the surface of doing indoor mapping for being able to do routing inside larger buildings. And one of the things that I found that I wanted was the ability to kind of model and visualize that space. And I haven't gotten very far on this project yet, but by using the SFCGAL extension that goes with PostGIS along with the X3DOM project, I've been able to pull data out of PostGIS, extrude it. The ST extrude function can take a 2D object and pull it out into 3D. And then the X3DOM project allows you to actually visualize all this in the browser. So I'm playing around with some different ways to go about that process. It's a lot of fun, and I'm really looking forward to seeing continued development and projects based around some of this technology. And one of the things I love about PostGIS is how well it works with QGIS. I absolutely love the QGIS desktop software for GIS applications. It is fantastic. And one of the reasons why I love it so much, I think, is because I have the ability to save my styles directly in the database right there with the database, the data itself. So this layer styles table will hold the style information from QGIS. And it's just a big blob of XML data. It's and so just it's pretty simple to store, but the fact that it's enabled and easy to do by default, and then you can back up your styles right there with your data. You don't have to rely on analysts to save their styles in the right place. I don't have to remember to back my own stuff up because I back up my databases. So this is a really cool thing, and I will show a little bit of how this works at the end of the demo. And on the note of the demo, it is time to switch over to dbeaver, and we'll start getting our hands dirty with some code. So this is the script that is available to download from the website. And feel free to follow along. If you do have questions about the code as I'm going through, if you can make a note of the line number that I'm on, the line numbers are displayed here on the left-hand side. That will greatly help me come back and answer the question if I've moved on from there. So that'll help me just get to the right place to answer your questions. So the first thing I'm going to do is just double check to make sure I've installed pgrouting. If you've loaded the demo data, you already have PostGIS and HStore extensions installed. They are required in order to get the data loaded to start with. And then pgrouting will be needed here in a little bit. And I just want to point out again, I love the if not exists syntax that Postgres has. Not all databases have this succinct syntax to allow you to try to create something, and if it already exists, don't worry about it. I can run this over and over and I'll never get an error. I think that's really cool. So this first code example, I'm going to run the code so we can see the initial results. What I'm doing to start with is I'm setting up the beginning of our routing problem. So I'm pulling out the start point that I've defined from natural point. We're pulling out just the peak that is South Table Mountain. So this is where I want to start my routing problem from. And I am joining to the roads data I'm casting a net that goes out 50 meters. So the std within function will allow us to select roads that are within 50 meters of the point that I've selected to get us those nearby roads. And we see down below, we have 2 rows that were returned. One is classified as a track, one is classified as steps. The line locate point function is the next column. So this function takes a line geometry, that's the r dot way, that's our road, and a point geometry. And what it's doing is it's telling us where on the line is closest to the point that I've also passed in. And so the result that we get is going to be a number from in the range of 0 to 1. If it's either 0 or 1, we know that we're at the end of a line. If it's a number like 0.387, we know that this nearest point on this line is about 39% of the way through the distance of that line. So that in of itself isn't super helpful, but we can pass that line locate point into line interpolate point. And it takes that number and the original geometry for the road, and it returns us the actual point that is on the line at that spot. I'm going to flip to the spatial tab here in the dbeaver output so we can see what this looks like on the map. We have, get zoomed in here, we have our center point here. This is the South Table Mountain peak that I pulled from that natural point table. And then we have this orange line. It looks like one orange line, but that's really the 2 different lines that we had together. And then the 2 blue dots indicate the result from that line interpolate point. So we can see that where it found those nearest points. This is very helpful to split apart your lines. And as we'll see as I go through this routing demo, my routing demo doesn't use this method. It uses a very simple nearest neighbor search. And what we'll see is that it's not perfect. And if you really do want those polished, perfect results, you're going to have to throw in some tricks like this to kind of split apart your strings or your lines and find the right start and end point for your route. So I've decided that I want that South Table Mountain point to be my starting point. I'm going to go ahead and just save that geometry here as the start point column in a new table. So we have a start point column in the table called My Route. And I'm going to build on this table as we go through. And this is much like I would do in a full production run, but normally instead of having one start point and one end point, I would have a large number of start and end points. But I find it's very helpful to materialize this information in a table, especially when you're going through the troubleshooting and exploration phases, because when something doesn't work right, your route comes out funky, your times are off, your costs are off. This allows you easy ways to kind of get in and figure out what's happening each step of the way. So we have our start point, but a start point isn't very good on its own. We need somewhere to end. So I'll alter my route table and add an endpoint geometry column. Then this next query will update that endpoint geometry column using the centroid function. So again, we're pulling a polygon. I want to get to this Pangea coffee roasters after I've been on this hike, but I don't want to try to compare to a polygon. I just want that point. So we use stcentroid to give us a nice single starting point. And I'll go ahead and run this query to take a look to see what we have inside the my route table. Flipping into the row view, we have the start point and the end point. And if I throw it over onto the spatial viewer, I go ahead and click here so you kind of can see where I'm looking. On the right-hand side, we have the South Table Mountain start point. And over here on the lower left side, we have this orange endpoint that is the inside of Pangea coffee roasters. So now we know where we want to be, where we're starting from, and where we want to get to. And at this point of any routing problem, you need to kind of consider how you're going to set up your cost model. Routing is largely driven based on costs. And so you need to define what that cost is. A lot of times we want the fastest route somewhere. And so speed is going to be a very applicable element of our cost. If I want to get there as fast as possible, I want the fastest route. You may want to use distance. That's pretty easy to do, and a lot of simple examples show distance because you don't have to work too hard to get to that distance of a geometry. You may have a preference on, I just specifically do not like this highway, so you could put a cost for certain highways extremely high to help the router go around that. There's a lot that you can do with your routing cost model. Whatever you do, it's best to set up a helper table, a lookup table that can store this meta information about your cost model. And so in this case, we have our road subclasses. I use this code column throughout. Anything that's based on the PGOSM project has this code embedded everywhere. So I use this code to join to my main data. And then I have the speed in miles per hour. You could easily set it up for kilometers per hour. That actually make math later on much easier. And then I have some Boolean indicators here for whether or not a road is routable for motorway, for motorized vehicles, or footway traffic. This allows me to select the roads that I want based on multiple attributes, not just the speed and costing kind of information. So this table, this routable table, will be joined to a number of times later on as we go through this example. Roads need prep for routing. That is a true statement. That is always a true statement. And you almost always have to put effort into cleaning and preparing your roads data before it's ready to be used in a routing project. I typically create a new table with a subset of my roads, as well as some specific attributes, cost information, other details I may want later on in the routing process. So I have this big long query here that creates this table, PGOSM routing roads. The columns it's selecting is grabbing some general attribute data, and then I'm calculating the cost as a function of length here, as well as renaming the geometry column from way over to the geom. Some of the PG routing stuff seems to expect the name being the geom. So I just kind of standardize that when I'm going into a routing phase, I re-alias my names to match where I'm working at that moment. So one of the first steps I do in these restructuring steps is I would always like to whittle down my data to the region that I'm actually working with. Now, the example data set that I'm using for today was already limited to 3 kilometers within Golden. So limiting it here again, it doesn't have a whole lot of value just because of the actual demo data I'm using, but I almost never have that small of a data set to start with. I normally have at least all of Colorado loaded, if not the entire US West region. And so if I'm doing a routing project here, locally in Colorado, and I have all of US West, there's a whole lot more work that the database engine has to do to get me those answers. So this can help save your performance, boost your performance quite extensively when you're working with larger data sets. And so once this subquery that gets me a nice compact envelope that I can use, I can now limit down my roads line with a simple bounding box filter here using the and sign. And then I'm joining to this routable table. As I mentioned, we're joining on the code column. But here, because I'm starting at the top of a mountain and I'm walking to somewhere local, I'm going to exclude anything that's a motorized path. So this will keep me on the sidewalks and the hiking trails and avoid the local city streets that are really intended for driving, not for my footway traffic. So I can go ahead and run this query. And when it creates the table, we'll see that we have 2,278 rows in the resulting table. So by limiting to the golden bounding box, we did limit out some rows of that road data. And then by limiting out, by excluding the motorized paths, we further whittled down the number of roads that we're working with. Routing problems are inherently complex, and so I'll keep saying it, the more you can whittle down your data and get it to really what you need for the problem at hand, the better your performance will be on any given hardware. And of course, don't forget the spatial index, the gist index should be created on your geometry columns as you're going around creating these new extra tables. Going to just ensure a couple these tables don't exist. The pgrouting functions coming up will recreate these functions. And if they already exist, they will fail. So I want to make sure they're out of the way first. So the first step to do now that we've set up our base roads data, we have a little bit more cleanup to do still. The roads data needs to be what we call noded. All of these long road lines that have other roadways that intersect in the middle of a line, if it's in the middle of a line, the routing algorithm will not pick up that it can actually deviate path there and switch over to another line. So what this node network, PGR node network function does is it looks at your roads data and you pass in what table you want it to look at, and it will find all of the potential intersections in your data and split that out into separate rows of data. And it takes a couple seconds to run on this small data set. If you have a very large data set, this can be quite expensive. And the result of running this function is you get a table with underscore noded at the end. It's the same table name here, just with the underscore noded. Once we have our noded roads layer up, we need to create the topology. This is how the routing functions know how it can get from this line to that line and from point A to point B. Is it creates this topology that maps out all of the different paths that it can take. And it goes and creates another new table. It uses the noded version and then adds vertices underscore PGR to the end. So we've now created 2 new tables in our database based off of that roads table that I had created. The last step you always want to do is run this analyze graph. This is a quality control step that is worth taking some time to get into and understanding. This helps, it checks all the different vertices that it knows about and all the different line edges that it knows about, and it looks for potential problems. And so one potential problem you could have is if there's a bunch of one-way roads that meet in the middle but no way out, it can detect that is an invalid setup. That look, if you drive on any of these one-way roads, you get to this point and then you can't leave. So it can highlight those. It can highlight dead ends. And some other problems. So if you want to find potential issues, you can query that PG underscore PGR table where that CHK column is more than 0 and inspect your data from there. For the sake of today's demo, sorry, I'm skipping ahead, quickly looking at the roads data that I generated, that was just the footways, versus the noded data. This just shows that we originally had about 2,300 rows, and once we ran it through that noding function, we ended up with about almost 6,400 rows. This doesn't mean that we have more geometry data. It just split the geometries apart into more rows of data. So just be aware that that does happen. And then one really nice feature about how all this works is inside of this noded table that function generated, it gives us a column called old ID. This old ID matches back to whatever was the ID column that it was built off of. And in our case, this was the OSM ID. So if I take a look, we're gonna walk through a few steps of this noded version. And if I select this first geometry here, I'm going to zoom in so hopefully you can see that little tiny blue line right between the intersection of these dotted red lines. So that is one portion of what was noded out. If I continue down here and just select one line at a time, we can see that we have some much smaller sections, and there's a lot of intersections where these small line segments end. So we can kind of walk through the segments there if we wanted. I can also select the full column, and we can get an idea of what that full original line looked like. And if we hadn't gone through the process to node the data, to split it out, this would be treated as two endpoints. There would be an endpoint on this side and an endpoint at the northwest side. We would not have any ability for any of these other paths that are up here to intersect in the middle. They would not be considered valid routes. So if you do need to ensure that you have the noding done, otherwise you won't have these valid routes. And if I'll run this query again, the second query, using OSM ID back on the original table. So this was loaded with the demo data. And if I flip out into row view, we can see we have a single row that is linked to this ID. And if I select that geometry, we can see there's that full line in its original glory before the noding was done. So we really did have it on truly one line. Okay, so now with our noded table created, I'm going to add a few more columns to it that I can use later on. We're creating one to store the length as the cost as a function of length, another one to store the cost as a function of minutes, and then another one to just store that code to make that PGOSM uses in order to make our joins work easily. So we've added 3 columns to that noded table now. This next query is simply going to update those 3 columns. What we're doing, we're updating the noded table. And because we have that old ID and the new ID, we can use that to join back to our routing roads table that I created. And that allows me to, one, get the code that I had stored in that table, which then allows me to join to that routable table. The length that we're calculating is a simple st length function of the geometry. And then the minutes uses that length again along with our metadata that we have for max speed based on the subclass of the road type. And then we have some other math that handles making sure that my miles per hour combined with the length in meters works out to be a time in minutes. And I'm relatively confident I haven't messed that particular math up. But if anyone finds that there's enough little steps in there that if I have made a mistake, I'd love to know so I can fix it. So this just goes through and updates and persists this data in our noded table so we can use it in the routing functions. Now, if you've done that analyze step and you've validated your data, you may have gone and done some cleanup. But what I am going to do here is do some cleanup in the form of deleting anything that doesn't have a source value. So this essentially means these roads are unroutable. And if you don't remove them from here, later on, the routing function itself will have a hard time with the null value. So I just go ahead and remove them. I've looked at this data, and for the case at hand, the data that we have removed is not pertinent to the project. So at this point, our road data is now routing ready. We are able to pass it into any variety of routing functions through PG routing. We have a little bit more that we have to do before we can run that route, though. We have to figure out where we're actually going to start and end our route on. So far, we know where I want to be. I want to be standing right on the peak of South Table Mountain, and I want to get to inside the coffee shop. So we have that established, but we don't have roads exactly to either of those places. So what we're doing now is finding potential start points. So this query here, we are pulling our endpoint, and I'm finding the 15 nearest points ordered by distance from our start point. So these are the 15 closest candidates for our routing function to be able to choose. And if I zoomed in just a little bit here, you can hopefully see that most of these are on these dotted red lines, which are sidewalks. So one of these dots is going to be the route that is picked by our simple nearest neighbor method. These particular nodes, these come from the vertices PGR table. Each one of these has a primary key associated with it, and I've brought it in the query as r.id. We can see it here. If I click on the data on any one of these points, we can see the primary key value for that row. This is the value that we need for the routing function. We need to know the ID of the vertice that we're going to start at. And because our routing needs to know the IDs for our start and end points, I'll go ahead and alter my route table one more time and add the start node and end node so we can go ahead and persist that data in with our table. And this helps make troubleshooting the start and end points of your routing algorithms much easier. Is if you actually save what you chose, it is a whole lot easier to come back and check to see what you did, and therefore why it did or didn't work the way you might have expected to. So we have our points, we have our start point and our end point, and then we have two null values because we haven't set those nodes yet, those node IDs. The next two queries will handle setting those values. I've basically taken the prior query where I was showing the top 15 nearest ones. Now I'm limiting it down to simply the first closest point. And in this case, I'm starting with the start point here. So I'm doing a D within on the start point against the geometry. And it's important to do some sort of limit on how far out you're going to throw your net for choosing your start and end point. If you happen to have a start point that doesn't have any valid routes within 10 miles, if you don't have a sort of limit like this, your algorithm will pick up that start point even though it's literally 10 miles away and run a route. It's going to be invalid because it's missing out on everything between where you are and where it chose for the start point. So I do recommend that you have some way of limiting nearby areas, that if there isn't anything within 200 meters, this point would be considered unroutable. So this will run and update the start node ID. The next one is the same. I've just switched. We're now looking at endpoints, and I am setting the end node ID. So go ahead and run that. So this next query, we're mostly looking at the data stored in my route. I have joined to the vertices table twice. Once so I can join for the start node, and another so I can join for the end node. But this will actually allow me to see what we're working with. So on the left here, I'm selecting the start point where that's South Table Mountain. That's where I'm standing. And I've also selected the point that has been chosen by our nearest neighbor search for where we're going to start. So we can see we got a point over here. I can do the same with the end point, and we get the center of that polygon. And route end, we can see that we got one of the blue dots on the sidewalk next to the building. So these are the points that have been chosen. I can select all four of these at once so we can kind of see the whole layout, start side on the right, end side on the left. Now we get to the actual routing portion. I'm going to go ahead and run this query so we can see the result. Let's get it in grid view first. So I've ran the query. The top portion in the select clause is quite uninteresting of this query. It's just pulling out some data for us to look at. The real magic happens inside this function. I call this the routing DJ. I'm not quite certain how to pronounce DIJKSTRA, so I've just always called this my routing DJ. So the DJ needs a query in the form of a string that's going to get it the data it needs in order to run. So this query, this is where you get to tell it what costing you're using. So if right now I have it set up with cost minutes. If I decided I wanted to find, you know what, give me the closest one as far as length, I could quickly switch this to cost length, and I would get a completely updated algorithm based on a different cost. The other parameters that the function needs are the node that it's starting at for the route and the node that it's going to end at for the route. And then the last one, the last bit that I have set to false is about directionality and one-wayedness. And so if I was in a car, doing a routing for cars, and I wanted to observe one-way signs like law-abiding citizens should, we would set this instead to true in order to get it to take the one-way street into effect. Considering this is a foot model, most footways don't have one-ways associated with them. I'm ignoring that for this particular example. And then at the end here, we're joining to the noded data, this that gives us some metadata, and then our routable for some more metadata. And then I'm ordering by this path sequence column. So this is going to force that the rows are in the order that they would actually happen in the route. So if I'm going to click on this first geometry here and fly out the side panel so we can see it. This first geometry is indicating that it's going to have us walk around the entire top of the mountain before we start descending down the stairs. The point that it discovered was right here at this junction. That's where it decided to start. And apparently we have to walk all the way around and over here to get to this. So this is obviously not ideal unless you want the panoramic view one more time. But from a routing perspective, this is where you run into limitations with a simple nearest neighbor selection methodology. Continuing down our route, I can select the next geometry, and we're walking down some big stone steps, and I can keep clicking through, can select a few at a time, and we can kind of see the way that this route is coming together. And if I select the whole thing, it'll pull up the whole route for us. Flip over to spatial, and now we can also see our start and end points as well. So we have the start point in blue up here, the orange line is our route, and then it routes us over here onto here. And if we can see that it is avoiding our city streets. It's having us walk down sidewalks. This is a good thing. It's a safety, I guess. And it's going to get us to where we need to go. Now, when I'm working on a project like this, I normally personally don't care about the individual steps other than making sure they're valid. But really what I care about is the aggregated route. What's the overall route look like? What's the overall cost? These are the details that I care about because I'm coming from this at a more of a large scale analytic perspective instead of a single end user going through, an app on their smartphone kind of perspective. So I'm not concerned about the individual steps. And so I've created a geometry to store my route information and cost information. And I've simplified the prior query. This is essentially the same query. It has a few less joins. And I'm also taking an aggregate of the cost here. I'm summing up the cost for each step into a total. And I'm doing the same with the geometry. I'm summing all my geometry up with this stcollect function as one single multi-line string. And this inner portion of the CTE, it's aliased here as A, gets used down at the bottom in order to do the update. So we're setting that cost minutes column that I just added to our aggregated cost. We're setting our route column that I added to the aggregated way. And then I'm using that aggregated way along with the stlength function to recalculate the cost length here. So I can go ahead and do that. It'll update my single row. And if I look in my table now, this my route table we've been building, we have our start point, we have our end point, and then we have this single column here for route that has our multi-line string. So we can see all of this together as one. And we can get back into the start and end nodes. So when I'm troubleshooting this later on, I go, I don't think that's right. I can actually get in here and look at these nodes to see what it selected and maybe work on improving that algorithm. And I also have the total costs in the form of minutes. Here it's saying it's going to take me just over 38 minutes to get there. And the overall length of that is going to be just under 2.4 kilometers because this data is in meters. So we have all of this data persisted here in a table. And now I'm going to switch gears just a little back to the layer styles that I promised. So layer styles table is our method of is a method of saving the styling information for QGIS directly in the database. So we have the table here, and this is included with the demo data. The table catalog is what database that it's expected to be in, schema name, table name. So this is all used by QGIS to figure out which layers should apply to which styles. And then a really neat option is the use as default column. So when this column is set to true and dbeaver visualizes that as a checkbox, when this layer is pulled into QGIS, it'll automatically grab the style information and apply it to the style, so you don't have to do that manually. And just a real quick peek into this style QML column. This is the raw XML that QGIS uses. We can see right here that it understands it's QGIS, and you can kind of see through it's just a whole bunch of gibberish related to styling. So I'm going to flip over to QGIS now. So I have a blank project up here, and I have already connected in my browser. I've connected to this database for Golden OSM demo. I'm going to refresh the catalog because I've been, dropping and recreating objects. So I want to make sure it knows what we've got available. And right away, I'm just going to go over to this public schema. And I see I didn't get my prior testing completely cleared out. But I can bring in this information from this my route table, and it'll draw, we've got the 2 points. It's the shape that we've been seeing all along. It's kind of nifty. More importantly, back to the styling information, is if I expand the golden schema where our source data is, I can say grab this building polygon. And if I drag it in, we get, and granted it's boring gray with some basic boundaries, doesn't look too exciting to start out. But if I zoom out from the map, what we'll notice is just there, it became much more transparent. The styling changed and the buildings became less prominent. And zooming out one more time, the buildings completely disappear. So I can tell that I have some zoom level based styling applied. This is super helpful for analysts working in this type of software. If they have to manually set up these style levels all the time, it's extremely time consuming. And a better example of that is going to be on this roads data. So I just brought in the roads line. The styles that were saved in the database automatically applied. I'm going to drag these down under our routing stuff. And as I zoom in or zoom out, we'll notice that, again, data disappears. Some of the sidewalk data, the less important roads have disappeared. As I continue zooming out, more of the roads disappear until we're left with just the major roads in the area. And these styles are quite complex to build. So that I just pulled up the properties that has the symbology for this. And these rule-based styles get quite complex because you have to have classifications for each type of subclass that you're styling. And each subclass has multiple layers of, over here we have the min scale and max scale columns. So if the analyst had to go through each of these subclasses and set up all of these zoom levels, that's extremely time consuming, error prone, and not fun at all. So being able to save this information directly in the database with the data makes getting to this end result much easier, where the styling just applies, and I could focus instead on getting my styling of these new layers set up so I can actually see what's going on here. I don't like spending time styling layers that I've already styled a dozen times in the past. So I can quickly copy and paste styles once, and just on the layers that are actually new layers. So I can make the start and end point more visible, for example. But diving into styling in QGIS is far beyond the scope of what we are talking about today. And with that, that is the end of the demo and the end of the session today and the end of the series. So again, thank you everyone who has signed in and joined along live for us with us today. If you have questions, please go ahead, start typing them in the chat, And I'm going to go ahead and mute myself for a little bit. And as questions come through, I will take care of them. Thank you.